The Bob Murphy Show, episode 468.
There's a tidal wave coming. What you gonna do?
Get ready for another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. It's your source for commentary and interviews conducted by a Christian and economist. Now here's your host, Bob Murphy.
Everybody, welcome back to The Bob Murphy Show. I am very happy to tell you that this episode is my interview of Steve Landsburg discussing his new book, Understanding Time and Space, which is all about special relativity. So it's Einstein's theory of what happens to the passage of time and the measurement of length when objects approach the speed of light. So this is a topic that has fascinated me since, junior high, and Steve's book made me understand it at a deeper level, and he's given us a little presentation here to give you a hint of what's in the book, so that this episode by itself is great, and I encourage you to watch the video version because he goes through a slideshow presentation that's going to make a lot more sense if you see it while he's talking. So it's standalone. You'll learn a lot just watching this episode, but of course, ultimately, I hope you do buy his book, and we give all the information at the end for where you go to get that. So without further ado, here is my discussion with the guy that you thought of as an economist, but here he's going to teach you some physics, Steve Landsburg. Steve, welcome back to the Bob Murphy Show.
Thank you so much for having me, Bob. It's one of my favorite places to be.
Oh, well, I appreciate that, and you're one of my favorite guests, so there you go. So what we're talking about, I can try to hold it up, but I think the background thing is going to eat it. Yeah, it's your book, Understanding Time and Space, and the subtitle is an invitation to the theory of relativity for anyone who is now or has ever been an inquisitive high school student. So we're going to be going through this, folks, and I promise you, I've been consuming any amount of a popular rendition, but also some fairly in-depth technical things explaining special relativity since junior high, and I really understood it at a deeper level, Steve, after reading your book. So I think you would accomplish what you're trying to, partly because some of the popularizers contradicted each other. And so it's like, well, okay, that doesn't help. So before we dive in, and so folks, I promise you, if this is something that interests you, I think you're going to understand it at a deeper level too at the end of this episode. But before we dive into that, can you just explain a little bit where this book come from?
Well, my hobby for the past 12 or 15 years has been answering questions about relativity on the internet under an assumed name. And
how did that happen? How did that?
I don't remember. Somehow I answered the first question and I used an assumed name for some reason I can't remember, and I just stuck with it.
Not to derail the whole thing, I have to ask you more. Is it like how Stephen King and J.K. Rowling both would write novels under different names to see, do I still have it? You didn't want people just to...
I don't think it was that. I think maybe some part of me was worried that the audience for my economics books would partly get turned off because they would say, "Oh, this guy's writing about relativity. That's not something I'm interested in, so I'm not interested in any of his books." I was afraid that people would not necessarily consciously, but kind of say, "This I don't happen to be interested in that. He's interested in that, so I'm not going to look at any of his books." I think that might have been what I was thinking at the time, but it's lost in the mists of history. I can't be sure. Anyway, I have not made a real effort to maintain that distinction. Anybody who looks at my anonymous answers about relativity, there are clues buried in them that will enable you to figure out who I am. But I've been doing that a long time, and I learned a lot. I've learned a lot about the best ways to explain things because it's on the internet, and people tell you immediately if you were hard to understand, and then you figure out a different way to say it. And a lot of people are very persistent, and they'll keep after you until you until you explain it in a clear way. I also learned a lot about what were the most common misconceptions, the things that people had picked up from other popularizations or had picked up from their physics courses that had not been taught the way I would have taught them. And the same misconceptions kept popping up over and over and over again. So I wanted to write a book that sort of led with, okay, here's a common misconception, don't fall into this trap. Here's a common misconception, don't fall into this trap. And I also wanted to sort of ground everything in the idea that relativity is really about the geometry of a possibly mysterious, until you've thought about it, place called space-time, in a way that is very analogous to the way an ordinary map is about the geometry of ordinary space that we walk around in every day. And that focusing on that analogy made it, I think, has helped a lot of the people I've talked to on the internet quite a bit in terms of clearing up the way they have of thinking about things. And so I wanted to write a book that emphasized all that.
Yeah, so for sure that latter point really is, I appreciated that you're right, and we won't steal your thunder. I know you're going to present some slides here, and maybe that's all baked into the cake, but some of the things that even with relativity, even though you quote know that this is what the theory says, it just feels nutty. And yet you were showing how, no, in a spatial context, that's not weird at all. It's like, oh yeah, it's common sense.
I'm kind of surprised that so many books on relativity, I was going to say no other books, but that could just be, there may be one out there that I don't know about. But as far as I've seen, no other books on relativity really emphasize this analogy the way that I did. And again, in my interactions on the internet, I have found that stressing this analogy almost invariably is the best way to clear up confusion.
Let me, again, before we dive in here, I'm just curious, so you're formally trained in mathematics, right?
I have a PhD in math, yeah.
So did you ever take any physics classes?
I've never had an economics class, and I've never had a physics class. So I'm self-trained in both things, which I think actually I've had a fair amount of success as an expositor of economics, and I'm hoping to have some success now as an expositor of physics. And I think a lot of that comes from the fact that I had to learn these things myself, and I know a lot of the pitfalls. I know a lot of the places where I went wrong when I was first learning these things, and where I had to struggle. And so I know what things seemed sensible to me at first, and I know what things seemed crazy to me at first. And so I'm maybe a little better to anticipate how the reader's going to react to those things and how to help them.
Okay. Well, yeah, and partly that's why I asked you, because it doesn't actually shock me that you said that, because I know in economics, like when you write on some issue, and I'm like, it's something I haven't read from Steve yet on economics, I know it's not going to be, oh yeah, I already saw that take from somebody else. Like the way you tackle it, like I might think you're totally wrong, but it's going to be fresh and idiosyncratic and, and very clever and subtle and whatnot and internally consistent.
I often feel that way about your writing. So.
Well, thank you. And so it doesn't surprise me. And that leads to my next question then, folks. I promise I'll let Steve teach you some stuff. Is it possible that you actually understand geometry a lot better than even a lot of the undergrad physics professors, and that's partly why? Oh,
probably, but I didn't use any fancy geometry in this book. I could have. I mean, there are ways to present relativity using some pretty advanced geometry. I didn't do that. This is all geometry that I think it requires some attention, but it doesn't require any insight or knowledge beyond what the average reasonably good high school student has done.
Right. Yeah. And I don't mean to intimidate. Look, folks, he really does deliver. It's not hard. It's like you could be a bright high school student and read this. What I mean though, Steve, is just like the comfort you had and say, oh, really? If you just think about it in terms of like people in a city block, turning right and left, the fact that to you it's so obvious that, it's the same thing in this setting. I can see how someone who just learned the rote formulas and just knew that, here's the Lorentz transformation and this is how you get the answer. And when you're at 0.95C, this is what your mass is, that they couldn't do what you did because they actually didn't see that connection. But
Maybe.
okay. All right. So is that enough chit chat? You want to dive into the slides?
Absolutely. Okay. So let me bring them up. This is my friend Alice, and I'm just going to double check. My cursor is visible there, pointing to Alice.
Yep, I see it moving around.
Okay, good. So this is my friend Alice, who is standing in a vast desert. There's no relativity here. We're not talking about time. This is just a map of a desert. And it's a pretty simple map because there are no significant landmarks in this desert. It just all looks the same, and there stands Alice. But Alice needs a way to find her way around the desert because she wants to bury her lunch pail in a particular place, and she wants to be able to find it again. So she needs a better map. And what she's going to do is, I have to figure out how to go to my next slide. Sorry. There we go. What she's going to do is impose some imaginary grid lines on this map. Or she could draw them on a piece of paper or something, but she imagines these grid lines in the desert. She is standing here. That's Alice, the little black dot. She's standing at a place that she calls the origin. She calls it the location that's distance 0 east-west and distance 0 left-right, distance 0 forward-backward. And with these grid lines, she can assign a pair of numbers to any point. She has discovered coordinate geometry. She's like Descartes. She is discovering coordinate geometry for the first time. And over here in green, this is the tree where she buried her lunch. And she can look at that and say, all I have to remember is from my home base, my lunch is, let's see, it's about 3.5 blocks to the left and 2 blocks forward. She's got this legend over here that reminds her which direction is which on her map. And she's set to go. Alice has a friend named Bob who is going to join her in the desert. And the thing about Bob, he's standing in the same spot where Alice is, but he's facing a different direction. And so Bob has his own map. Bob has his own map in blue. It's no better or worse than Alice's map, but it's different because he views forward as this way, and forward and backward as the way my cursor is moving now. Left and right is the way my cursor is moving now. Alice would call those diagonals. Bob, you can see the two different legends there. They call them different things. Whose map is right? Whose map is wrong? Answer, Alice's map is more convenient for Alice, given the way she's facing. Bob's map is more convenient for Bob, given the way he's facing. And that's pretty much all we can say about it. They're both equally good maps. They both recognize that these maps are equally good. Notice that Alice could change, and I call these sets of grid lines, these maps, I call them frames. Alice could change her frame, her preferred frame, just by turning around. If she turns from facing the way that we're now calling forward and faces backward instead, all of a sudden that tree is going to be not 3.5 steps to the left, but 3.5 steps to the right. It's still 3.5 on her old left on her old map, but it's to the right on her new map. If Alice were very naive, she might say, wow, this is weird because that tree was 3.5 blocks to my left, and then I turned around and suddenly it's 3.5 blocks to my right. Just by turning around, I made that tree move 7 blocks. That's incredible. But we all have enough experience in the world not to be confused by things like that. The tree did not move. What happened is that Alice changed from one map to another. And that's going to be a very important lesson as we learn relativity. A lot of times, people's descriptions of the world are going to change. It doesn't mean the world has changed. It means they have changed to a different description of the world. So now, let's bring time into the picture. Here is Alice, and she was in a 2-dimensional desert. But now, to simplify things, I'm going to put her on a 1-dimensional street. Here she is in New York, standing on 6th Avenue, and where my cursor is, this is 47th Street, 48th, 49th, 50th, 51st, and so on. But this bottom line here, this is 56th Street at 12 o'clock. She has also drawn a line that represents 56th Street at 1 o'clock and 56th Street at 2 o'clock and so forth. So her map now shows...
Do you mean the avenue?
Avenue, sorry. I meant to say avenue. She's on 6th Avenue is what I forget what I just said. Whatever I said, I meant 6th Avenue.
Yeah.
She's on 6th Avenue at 12 o'clock. This is 6th Avenue at 1 o'clock, 6th Avenue at 2 o'clock, 6th Avenue at 3 o'clock. So her map now is showing not places, but events. This point here represents whatever event takes place at 48th Street at 2 o'clock. This point here represents whatever takes place on 51st Street at 6 o'clock. There's a concert coming up tonight at 6 o'clock tonight at Carnegie Hall on 57th Street on 6th Avenue. There's going to be a concert, and that concert is represented by this point here. The red line. The red line is Alice herself because she's standing still on that corner. She stands on 52nd Street. That's where she is at 12 o'clock, where she is at 1, where she is at 2, 3, 4, 5, 6.
And just for people to be clear, so she's at the corner of 6th Ave and 52nd Street.
She's at the corner of, yes, this is a map of 6th Avenue. She's at the corner of 52nd Street on that map of 6th Avenue. She's there at 12 o'clock. She's there at 1 o'clock. She's there at 2 o'clock. She's there at 3 o'clock. This point represents Alice at 12, Alice at 1, Alice at 2. I think of the entire line as representing Alice. This line over here, the green line, is Carnegie Hall. That's where the concert's going to be. That's at 57th Street. And Carnegie Hall is always at 57th Street. At every time, it's at 57th Street. So the line is Carnegie Hall. Carnegie Hall is a line. The concert is a point on that line because the concert takes place at one particular time. Yeah. Carnegie Hall is there at all times. The concert is there at one particular time. The blue line is Bob, who is skateboarding down 6th Avenue pretty slowly. It takes him at 12 o'clock. He's halfway between 50th and 51st. By 1 o'clock, he's made it to 51st. By 3 o'clock, he has made it to 52nd, where he passes by Alice and gives her a high five, and so on. And he then is represented by this blue line. This is we call this a space-time diagram. We've got a frame on there. We've got those grid lines so that Alice can give names to the various points and places.
Can I stop you for a second just to make sure we don't lose people, Steve? So here, if you were in a drone above the city looking down, Bob would be, quote, going straight, according to you, just going up 6th Avenue, up, 50th, 51st, and so on. It looks diagonal here because you're showing like the time as one of the dimensions. And
right. Bob is moving this way. He's moving back and forth along 6th Avenue. But the map, the picture shows where he is at 12 o'clock, where he is at 1 o'clock, where he is at 2 o'clock, where he is at 3 o'clock. That creates a diagonal line. That doesn't mean he's traveling diagonal.
Okay, great.
Those grid lines there are Alice's frame. It's how she describes the world. Bob, however, has every right, and this is what we call the first principle of relativity. As long as Bob is traveling smoothly at a steady rate, he has every right to claim that he is standing still and that Alice and 6th Avenue and Carnegie Hall are all moving to the left. He has every right to say, if he wants to, and this takes a little getting used to, but if you think about it, if you're riding in a car, in a very smooth traveling car, you could say to yourself, okay, I'm sitting here in this car and all the trees are traveling past me. That's how it looks to you. And nobody could prove you wrong if you claim that. It's a perfectly good way of describing the world. This is something that was known at least to Galileo. It goes back way before Einstein. So hundreds of years ago, several hundred years ago, people were aware. Again, Galileo was probably the first who was explicitly aware of it. That as long as you are on a skateboard or a car or a ship or, Galileo probably didn't think about skateboards and cars, but whatever, as long as you're traveling at a smooth rate, you are entitled to claim that you're the one who's standing still, and all the other things that claim they're standing still are actually moving past you. So if Bob is going to describe this particular situation, he's going to have his own frame. His frame, oh my, have I think there's a slide I should have included and didn't. But he's going to have a frame where he's going to consider this line to be all at one location. This is Bob's location. And he's going to have other lines parallel to that. Again, I wish I had included one more slide. There are going to be other lines parallel to that blue line that represent other locations. In other words, he's going to say 52nd Street is not a fixed location. 52nd Street is constantly moving to the left. But the fixed location is where I am. There's another fixed location that is a block to the right of where I am, and that fixed location is represented by another diagonal blue line. And there's another fixed location that's represented by somebody moving the same way I am, starting at 53rd Street, and that's going to be given by another blue line. But he's going to say 1 o'clock is 1 o'clock, 2 o'clock is 2 o'clock, 3 o'clock is 3 o'clock. I agree with Alice about all that. So if Bob were to draw a frame here, it would have a bunch of diagonal blue lines, but the horizontal lines, and they would take the place of Alice's vertical lines, but the horizontal lines would be the same in Bob's frame and in Alice's frame. And that's exactly how Galileo understood relativity. It's how everybody understood relativity prior to Einstein. It turns out that's wrong. And it turns out the reason that's wrong is that as a matter of empirical fact, everybody agrees on the speed of light. Now, let me say what I mean by that and why it's so remarkable. If Bob has a baseball in his pocket as he skateboards along the street, he's going to say, I am standing perfectly still, and my baseball is standing perfectly still. Alice is going to say, no, that baseball is moving. That baseball is moving at, I guess on this map, a half a block every hour. She's going to say the baseball is in motion. Bob is going to say the baseball is still. If Bob is traveling to the right at 10 miles an hour, according to Alice, and a baseball is traveling to the right at 15 miles an hour, according to Alice, Bob is going to say that baseball is traveling to the right, not at 15 miles an hour, but at 5 miles an hour. Bob is moving 10 miles an hour, according to Alice. Bob's moving 10 miles an hour. The baseball's moving 15 miles an hour. That means the baseball is getting away from Bob at 5 miles per hour, and Bob is going to say that baseball is traveling at 5 miles per hour. Alice says 15, Bob says 5. The remarkable fact is that when Alice and Bob both measure the speed of light, they don't get different numbers. They get the same number. And that is a fact that we know from many, many experiments. And if Bob's frame were the way I described it just now, we would get Galilean relativity. We would not get a version of relativity. So I think I can make that clearer by going to the next slide. Here in red.
Can I stop you, Steve?
Sure.
Let me just make sure they got the baseball thing, maybe a more intuitive one, because it's like, how could a baseball be going 5 miles? But like, if someone's standing still watching a train go by, and there's a pitcher inside the train car at like the left end of it, looking forward towards the front of the train, and then the pitcher, he thinks he's just standing there still inside the car, and he throws 100-mile-per-hour fastball, according to him and the guy who's catching on the other end of the car. And then the person sitting there is watching the train go by, and they think the train's going at 50 miles an hour. They're going to think that ball is moving at 150.
Absolutely.
But what you're saying is, if instead, though, there's a guy on the left end and he turns on a flashlight and a photon comes out and he thinks it's going at the speed of light towards the front of the car, and then someone standing outside sees the train going at 50 miles an hour and then also sees the light, moving much faster than the guy is, they're also going to measure that speed of the photon as exactly the speed of light, the number that it is.
That is correct. And if you're hearing that for the first time and it doesn't sound mind-blowing to you, then you haven't understood. anything, any of the normal things we know about uh, uh, behave the way that baseball does. The person on the train is going to say, I just threw that baseball. I'm going to repeat your example. I threw that baseball, it's traveling 100 miles an hour. The person on the platform is going to say, well, no, that ball is traveling 150 miles an hour. You, the thrower, are traveling at 100 and the ball is traveling at 150. If you throw a photon rather than a baseball, remarkably, both observers are going to agree about how fast it's moving. And all of relativity is really about understanding how that can possibly be.
And maybe we should just say too, part of the reason this didn't jump out at people hundreds of years ago is because light goes so fast.
Absolutely.
And what is it, like 186,000 miles per second?
Mm-hmm. Yeah. So,
which, folks, if you think about that, like that's very fast for like, for terrestrial things.
It's probably something like 6 times around the world in a second.
So that's partly why you like the discrepancy between, oh no, is it 186,000? And of course we're rounding miles per second plus 50 miles per hour or not, you know what I mean? Like the difference between those two is so negligible. That's why it wasn't jumping out at people. Exactly. Whereas with baseballs, if it was like, no, a baseball is always the same speed. It always seems to be going 87 miles per hour, no matter who's looking at it, then that would be weird. And we would notice what the heck is going on.
Yes, so, that would be, we would be living in a very different world then. Let me pause at this moment to say that these pictures are coming from the book. I've got a few at the end that are not from the book, and I'm going through them, and I'm doing my best to be clear and understandable, and I hope I'm succeeding. And you are certainly helping with your interjections, but this goes by considerably slower if you're reading it in the book, and it goes by slower. And there is a lot more explanation than I'm giving. I'm hitting the high points here. But if you're reading the book, all of this stuff is presented quite a bit more gently and with quite a few pauses to say, you might be thinking this. If you are, then you're making the following mistake. Here's how to think about it better. I know some people prefer videos to reading, but for this stuff, I think if this is going by a little too fast, if you're not sure you're understanding, I promise you that reading the book will be a different experience. I'm going to jump right to showing you what the correct frame is. This is space-time again. Alice is standing somewhere where this could be 6th Avenue, but I've just I've changed it to just a place where there are locations, which she calls 0, 1, 2, 3. These are mileposts. This is a milepost that says x equals 0, a milepost that says x equals 1, x equals 2, x equals 3. And this red line is the street on which Alice is standing at a time that she calls time 0. This is the same street at time 1. This is the same street at time 2. This is the same street at time 3. Ignore all the blue stuff for now. We'll just understand what Alice is doing. This is a map of her space-time. It's a map that shows there's one street that she's on. She's on a single one-dimensional street. We've really simplified this. She's not in the desert anymore. She's on a one-dimensional street. At every vertical level, we have another picture of that street at a different time. This is Alice herself. She is standing still at location 0. She's there at time 0, she's there at time 1, she's there at time 2, she's there at time 3. That's Alice. When she moves this direction on the map, she's moving toward the future. If she were to move back this way, she's moving toward the past. This is to the right, and this is to the left. This blue line here is Bob, who is skating past Alice. At time 0, they're at the same place. At time 1, he's moved a little to the right. At time 2, he's moved further to the right. At time 3, he's moved further to the right, and so forth. He considers all of the places he's been as being the same place. He says, I'm standing still. He calls this line location 0. I've used the variable x for Alice's location, the way she describes it, x prime for Bob's location, the way he describes it. Alice says this red line is location 0. This red line is location 1. This red line is location 2. Bob says, no, this blue line is location 0. This blue line is location 1. This blue line is location 2. These are Alice's times. This line represents the world at a particular time. This represents the world at a later time. This represents the world at a later time, times 1, 2, and 3. For Bob, we have these blue lines. This represents the world at time 0. This represents the world at time 1. This represents the world at time 2. That's how Bob sees the world. That's how Alice sees the world. Now, I haven't related this yet to the speed of light. I will. But I just want to understand what this map means. Everything is in this map. All of relativity theory is in this one picture. And if we can understand this one picture, we're going to understand everything.
And maybe you were getting ready to say this, but is it correct that for Alice, all the things at time 0, that's showing all the events that are occurring simultaneously?
Yes.
In different locations at time 0, and the same for time 1? And
yes. So those are for Alice, the horizontal lines. This is the world at time 0. Everything, this is the world. This is a snapshot of the world at time 0. So every event that's taking place in this snapshot is taking place at the same time. They're all simultaneous. This is a snapshot of the world at time 1. And if we see a little a bug getting run over by a car at this point, and we see a tree falling at this point, if they're happening at this point and this point, it means they're both happening at time 1, so they're happening simultaneously.
According to Alice.
According to Alice. If we take a snapshot at time 2 of the world, I'm describing everything now just in Alice's view. Everything on every event that is on this line here all takes place at time 2. It's all simultaneous. But Bob does not agree that those events are simultaneous, because he says, actually, the world at time 1 looks like this. Here's a bug dying. Here's a tree falling. Alice says those things happened at the same time. Bob says, no, they happened at very different times. Alice says this happened at time equal 1. Coincidentally, Bob says it happened at time equal 1. Over here, we have something that Alice says also happened at time equal 1. Bob says, no, that happened actually before time 0. Looks like it happened about time minus 1/2. Because time 0 is all along here, and that happened below time 0. They do not agree on the times at which events take place. That's the big innovation. That's the big change from relativity as it was understood pre-Einstein. Pre-Einstein, we understood that Alice and Bob disagree about locations. Alice says, I'm standing still. Bob says, no, you're not standing still, you're moving. We understood that they disagreed about space. The innovation in Einstein's version of relativity is that they also disagree about time. They will assign different times to different events. Now, does that mean that they're living in different realities? No, it means they have different maps of the same reality. They both agree that the bug died. They both agree that the tree fell. But when Alice has to assign a location and a time to one event, she does it using her red frame. When Bob has to assign a location and a time to the same event, he uses it using his blue frame. He does it using his blue frame. And in general, they're going to assign different locations and different times to the same event. Neither of them thinks the other is wrong. They each think that they are using the frame that is most convenient for them, the frame that comes naturally to them, the frame that looks right to them. They understand that the other frame looks right to the other person. Just as when Alice faces one way in the desert and says, my lunch is to the left, and Bob faces the other way and says, no, your lunch is to the right. They both understand they're not disagreeing about where the lunch is. They just have different preferred ways of describing where the lunch is. And in this map, this is a map of the world at different times. Alice and Bob, they completely agree on everything that happens, but they choose to describe those events. They choose to describe the history of the world in different ways. Alice says she goes here. Bob says she goes here. Bob says she goes here. Alice says she goes here. Bob says she goes here. Alice 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 says she goes here Let's see if we can figure out what this is. According to Alice, this is at a location that's a little more than 2, because 2 is here. It's a location that's a little more than 2, and it's at time 3. Bob says, no, it's at location 1, because that's my location line, and it's at time 2, because that's my number 2 timeline. Alice says location a little more than 2, time 3. Bob says, no, location 1, time 2. Are they disagreeing about anything substantive? No. They are adopting different ways to describe the world, and those ways of describing the world are the ways that look natural to them.
Can I stop you?
Yeah.
I want to just make sure people understand, though, how profound this is going to be, and that's why I stress the simultaneity, that we're not or Steve is not merely saying, folks, that it's different conventions, and that the same event, one person says, oh yeah, with my coordinate system, it's, these are the axes of where it's located, but you could have a different origin, so yours is different. And, I might say it's 3 p.m., but you might say it's 6 p.m., and you might just think it's like time zones or something. But no, that's for the simultaneous, like, people around the world could disagree on what the time is right now, but like when New Year's Eve hits and the ball drops in, Paris or something, and then later it drops in New York, everybody agrees it dropped first in Paris and then New York. They might have put different labels on what the time was, but here we're saying, no, Bob thinks certain events happened at the same time, whereas Alice thinks, no, some of them happened sooner than the other ones did.
Absolutely.
Okay.
Absolutely. And we're going to, I promise you, a couple slides from now, we're going to see some very profound consequences of that.
Yes, I just want to make sure people weren't just thinking you were spending a lot of time just talking. Yeah, I get it. People could put different labels on something. Give me a break. So
I just want to tie this to what I said earlier about the speed of light. In fact, maybe I should not have even mentioned the speed of light until now. But here we go. This is a light beam. Bob is passing Alice at this point that they've both called the origin. And just at that moment, Alice shines her flashlight down the street. Light travels, I've chosen units here in which light travels at speed 1. Mm-hmm. So if time is measured in second, then x equals 1 is 186,000 miles to the right, and x equals 2 is 186,000 miles to the right of that. Choose whatever units you want to call the speed of light 1. That beam of light is going to be represented by this gold line. Remember, it's not traveling diagonally, it's traveling straight down the street, but it shows diagonal on the map because this is where the beam of light is at time 0, time 1, time 2, time 3. And if Alice tries to figure out the speed of that beam of light, she'll say, well, it left from 0, 0, and it passed through this point here. This point, location 2, time 2. It took the light, I'll call these seconds and blocks, although they're, I'll just call these blocks, and each block is the length that light travels in a second. She says it took 2 seconds for the light to travel 2 blocks. It must be traveling at a speed of 1 block per second. Again, they're very long blocks, but she looks at this, she says, she's looking at the point where my cursor is right now. She says that light traveled 2 blocks in 2 seconds. It must be traveling at speed 1. Bob looks at the same point and he says, no, actually it traveled what are the coordinates on that point? It's a little, x prime is a little to the right of that, so it's a little more than 1, and the time is just a little above this t prime equals 1 line. He says, no, it didn't travel 2 blocks in 2 seconds. It traveled a little more than 1 block in a little more than 1 second. Its speed must be 1. They look at the same, so the light, let's say, is hitting a screen here. And they're both observing the light hit that screen. Alice says that light left me 2 seconds ago, and the screen is 2 blocks away. It's traveling at speed 1. Bob says, no, that light left a little over 1 second to go, and it traveled a little over 1 block. It must be traveling at speed 1. The thing about these particular frames is that they always lead Alice and Bob to agree on the speed of light. The frame is constructed to make that happen. And what's the logic here? We started with the empirical fact that everybody measures the same speed of light. And then we built a frame, we built a pair of frames, one for Alice, one for Bob, that would yield that conclusion, that would be consistent with that observed empirical fact. And these are the frames that work. There's a lot more in the book about, there's a long appendix on how you could have invented these frames for yourself, but let's just take it as given. These are the frames that work, and these are the frames that that define the entire theory of relativity, and everything follows from this. So let's.
Can I just stop you? So just to connect it back to the Galileo discussion, Galileo recognizing the relativity of people's spatial orientations and relative speed and so forth, and that, you know, there's no privileged observer, but thinking time is kind of the same to everybody, and would think, yeah, a baseball, if I see it going 100 miles per hour and you think you're in a train and I think the train's going 50, then it's 150. If that were the way the world worked, you wouldn't draw the things like this. And
Correct.
In that world, the photon would be 186,000 plus 50 miles per hour.
Galileo would have said that for Bob's frame, these blue lines, x prime equals 0, x prime equal 1, x prime equal 2, those are the right lines. Those are the lines that show fixed locations for Bob.
Mm-hmm.
But he would have said, these lines, the timelines, those are wrong. Bob's timelines are the same as Alice's timelines. Bob shares these horizontal fixed timelines with Alice. Galileo would have said the right way to draw the frame is keep these diagonal lines for the fixed locations, but use the same horizontal lines that Alice uses for the fixed.
And that's why they would have agreed on simultaneity of events.
Yes.
In the get
that's
right.
why they would have agreed.
Which
they would have had the same timeline. They would have assigned the same times to all the
which matches our everyday intuition.
And they would have agreed on simultaneity, which matches our intuition.
Which makes, you know, oh geez, if you're facing a different direction, what I think is to the right, you can think is to the left, no big deal. But people don't normally think what I think happened first and then subsequently you can't think the other way around. How could that be? You know, because time seems like it's more, you know, objective or something than the arbitrariness of what direction I'm facing. Okay.
So I've been stressing that this is all, you know, it sounds like it's all conventions. They're not disagreeing on anything substantive. They're just giving different names to different events. And yet, that fact alone ends up having remarkable consequences for the way things work in the world. And I think we're ready to go on to that now.
And can I just stop you one last time? And I saw somebody remark one time in a book, and I'm curious, do you agree that it's funny? Like the thing that's really critical about relativity is that the speed of light is not relative. That's like in a sense, like everyone, you know what I mean? And so that's kind of funny that that's the linchpin around which the whole thing revolves. And yet, so, okay.
Yes.
Let's take a break from the action, folks, for me to remind you, if you like what you're hearing on the Bob Murphy Show, and come on, is there really another podcast like this out there? I don't think so. If you like what you hear, I encourage you to support it. Go to bobmurphyshow.com/contribute. Every little bit helps. I really appreciate it. bobmurphyshow.com/contribute. All right, let's get back to the show.
Here I've stripped these frames down to the little bit I need. Here are Bob and Alice at the origin. They're just parting ways. Bob has just hugged Alice goodbye, and he is going to travel to the right at 0.6 of the speed of light, and he's going to travel to Barnard's star, which is a star that's about 6 light years away. So it's at location x equals 6. Barnard's star sits there 6 light years away from us, according to us, and therefore it is represented by this vertical line, 6 light years away at time 0, 6 light years away at time 6, 6 light years away at time 10. That's where it sits. According to Alice, And according to Alice sits here on Earth, location 0 at time 0, at time 6, at time 10. She's always on Earth. So this red line is Alice. The blue line is Bob. He starts on Earth, and after a while, he ends up here at Barnard's Star. I've drawn just a couple of the red lines from Alice's frame and a couple of the blue lines from Bob's frame. He starts here at A. He travels to Barnard's Star, and these are some of his fixed timelines. This is so he says that this line is all at one location. And instead of Alice's horizontal timelines, he says that all of these events take place at time 0, and all of these events here take place at time 8. Where did I get time 8? The book explains very carefully how you calculate that 8. I think it's a little bit, it's less conducive to video than some of the other things. So I'm just going to ask you to believe me that if you draw the frame correctly, this line is labeled with an 8. Now, again, the book explains very carefully where that 8 came from. So Bob travels from here to here, and he says, it took me 8 years to get here. It took me 8 years to get here. I'm 8 years older than I was when I left. And because Bob has every right to describe the world according to his frame, he really is going to be only 8 years older. All of his biological processes will have advanced 8 years. Bob correctly says that 8 years passed for me as I traveled from Earth to Barnard's Star.
And like if he had a stopwatch or, a very intricate timekeeping device, it would have clocked the passage of 8 years.
Absolutely. It would have clocked the passage of 8 years. Now, according to Bob, what's happening on Earth when he reaches Barnard's Star? What's happening on Earth? We have to look. This shows the entire world at time 8. I asked what happens on Earth at the moment when he gets to Barnard's Star. Answer, he gets to Barnard's Star at time 8. So we have to ask what's happening on Earth at time 8, which means we have to follow this line back. And we discover that Alice's clock says 6.4 years have passed. So Bob, when he arrives at Barnard's Star, says, what's happening on Earth? What's happening on Earth is that Alice has aged only 6.4 years. Alice's clocks must have been running slow. Alice's clocks must have been running slow because I left at time 0. Right now at time 8, right at this moment means anywhere along this line, I'm 8 years older. She's 6.4 years older. She must be because according to her, only 6.4 years have passed. So she has only aged 6.4 years. Her clocks must have been running slow. What does Alice say is happening at that time? Alice says, when did Bob get to Barnard's Star? He got to Barnard's Star at time 10. She looks along a red line to see which things happened at the same time. Bob looks along the blue line to see which things happened at the same time. Alice looks along the red line to see which things happened at the same time. Bob says, I arrived at Barnard's Star when Alice turned 26.4 years old. They were both 20 when he left. Mm-hmm. He says, I got to Barnard's Star when I was 28, but she was only 26.4. We used to both be 20 at the same time. Now I'm 28, she's 26.4. Alice says, no, those two things didn't happen at the same time. These two things happened at the same time. I look along the red line to see what happened at the same time. You turned 28 when I turned 30, 10 years after I was 20. Your clock was running slow. Mm-hmm. And so this picture and understanding this picture is a long way toward understanding relativity.
Yep, this is great. And let me just stop you. So, again, folks, the intuition is that nobody's privileged. And so if you buy the principle that in order to make this stuff work, one of the implications, for everyone sees the speed of light is the same, regardless of their inertial frame. One of the implications is that time apparently passes slower for something that's moving relative to you. And so because from Alice's point of view, she's staying still on Earth and Bob's going, what is it, 3/5 the speed of light? Is that what the numbers are?
Yes.
He ages more slowly. So that's why from her point of view, when she ages, it takes him 10 years to get there. And so she's 30. And so from her point of view, he's aging more slowly. And so that's why he's only 28 when she's 30. But from his point of view, he thinks he's at rest and Alice is zipping away and Earth is zooming away at 3/5 the speed of light. So he has to see her aging more slowly or think she's aging more slowly. And so that's why when he gets to his destination, yep, I'm 28 now. She has to be younger than him from his point of view. And it sounds like we're contradicting each other, but we're actually not.
Absolutely. Look, Bob says that Alice's clock runs slow. Alice says that Bob's clock runs slow. And again, when people first hear that, they say, how can that be? How can they both be right? Well, when Alice and Bob stand on the street facing each other, and Alice says Carnegie Hall is to the left, and Bob says Carnegie Hall is to the right, they appear to be contradicting each other, but they're both right. They both have different ways of describing things. Everybody agrees that Bob traveled to Barnard's Star. Everybody agrees on, what he did when he got there. He planted a flag, whatever he did. They disagree, and everybody agrees that Alice had her 26.4th birthday, and everybody agrees that Alice had her 30th birthday. They disagree on which of these things happened at the same time when Bob landed. Mm-hmm. Alice says, my 30th birthday happened on the same day Bob landed. Bob says, no, your 26.4th birthday happened on the same day when I landed. Sounds weird, but it is no weirder when you think about it than the fact that Alice can say Carnegie Hall is to our left. Bob can say Carnegie Hall is to our right. They're using different maps. They're using different maps to describe the same reality. And once again here, they're using different maps. They're laying different grid lines down on the same picture. And once again, this is going to make it sound like the whole thing is just trivial. It's going to turn out that it's not. It's going to turn out the thing has profound consequences. And yet at this point, really, nothing that remarkable has happened. All that has happened is that Bob laid one set of grid lines down on the world. Alice laid a different set of grid lines down on the world. They each use their own grid lines to describe what's going on. And those descriptions are different. No big deal. Things get much more interesting, though, when Bob decides to return from Barnard's Star. Because when he returns from Barnard's Star, he is now moving in a different direction. And if he's moving in a different direction, he's going to have completely different grid lines. Those grid lines are going to describe the world in yet a third way. We have Alice's grid lines. We have Bob's grid lines when he's traveling outbound. And now we're going to add Bob's grid lines when he's traveling inbound. The green ones. Here, the blue line is Bob going out. And these other blue lines are part of his grid lines when he's going out. This green line is Bob returning to Earth. And when Bob returns to Earth, he now has these grid lines representing various particular times. How did I know exactly how to draw those lines? Again, it's all in the book, and it's much easier than you might think it is. It's just a couple of rules for how you figure out how to draw these grid lines. For the video, I just have to ask you to believe me, but there is no mystery when you read the book. It's the lines are not just coming out of nowhere. It tells you how I drew them. This is how they end up looking, though. Now what happens? Bob gets to Barnard's Star, and he says, I wonder what's going on Earth right now. He says, oh, I have to look along this blue line. I see that Alice is 26.4 years old right now. And then suddenly he takes off from Barnard's Star. He's going this direction, and his grid lines have changed completely. He has now he has these green lines. This line tells him what's happening right now. He's still on Barnard Star, just taken off, but he's now at his new speed, traveling back to Earth. And now he says, if I want to know what's going on Earth, I have to use this green line. Oh, I see that Alice is 33.6 years old. 20 plus 13.6. Alice has gone. Alice, a moment ago, Bob was saying she's 26.4. Now he's saying she's 13.6. And I want to just stop and say a few words about that. Bob turned around. He was traveling toward Barnard Star. Now he's traveling away from it. An instant ago, he said Alice was 26 years old, approximately. Now he says Alice is 33 years old. So it appears that Bob is saying that Alice aged like 9 years. Why? Because he turned around. If he hadn't turned around, her age would not have jumped like that. That sounds pretty strange. But think about this. When I stand in Chicago facing north, Los Angeles is 1,000 miles or more to my left. If I turn 180 degrees, Los Angeles is 1,000 miles or more to my right. Now, if I describe that to somebody, if I say I was standing in Chicago, Los Angeles was 1,000 miles to my left, I turned around, and now Los Angeles was 1,000 miles to my right. That person could say, whoa, wait a minute. You're saying that by turning around, you can make Los Angeles move 2,000 miles. And I'm going to say, well, no, I'm not saying that. I'm saying when I turn around, my natural description of where Los Angeles is changes. I'm not claiming Los Angeles moved. Bob is not claiming that Alice's age jumped. He can't, obviously, just by turning around on Barnard Star, he can't cause her to age several years. What he is saying is, I'm using a different map now. On my old map, she was 26 years old. On my new map, she's 33 years old. Her age is, when I'm outbound, I like to say that these two things happened at the same time. When I'm inbound, I like to see these two things happened at the same time. So now I say, an instant ago, I said she was 26.4. Now I say she's 33.6. And then he continues to travel home. And over the course of that time, it was time equal 8 when he left. It's time equals 16 when he gets back. His outbound trip took 8 years. His inbound trip took 8 years. So his total trip took 16 years. When he left, Alice was 20. When he gets back, Alice is 40. T equals 20 according to Alice. Bob's outbound trip took 8 years. His inbound trip took 8 years. According to his new inbound map, he arrives home at time 16. That tracks. He's home at time 16. He's aged 16 years. Alice has aged 20 years. When Bob gets back from his trip, he is 16 years older. Alice is 20 years older. And so this is a real actual fact about the world. You can't just, and somehow it is all predicted by the fact that they use these different maps. And yet this is not just a fact about maps. This is a fact about actual physical aging. Bob has aged less than Alice has. Bob, at every point along the way, says that Alice's clock is running slow. But at one point along the way, he suddenly changes his mind from saying she's this old to saying she's this old. And that enables her to actually be older when he gets back than he is. Alice says, Bob's clock is running slow the whole time. Alice has an easy story to tell. His clock was running slow the whole time. That's why he's younger than I am. Bob has a slightly harder story to tell. He says her clock was running slow the whole time, but there was one point there where I changed my mind and said, I don't want to say she's this old. I want to say she's much older. Sudden jump in the age that I attribute to her. And somehow that ends up actually meaning that Alice is substantially older than Bob when he gets older.
Okay, great. I mean, when I hit this part, like that resolved. I had never gotten that, all the expositions I had read beforehand, it was crystal clear. Yep. The whole time Bob's going to the star, he thinks Alice is aging more slowly than he is and vice versa. And then on the way back from the star, he also thinks she's aging more slowly than he is. And yet when he steps out of the spaceship and they shake hands or hug, they both agree, wow, Alice, you're older than I am. And so I never could get, how does that, and so you doing that, like it's a one-shot adjustment there. So that, because I had read other people say, well, it's actually not symmetric because he feels the ship accelerating and stuff, and which didn't really answer. Okay, but so anyway, so that was great. I guess, is now the right time for me to ask you, can you give us more as to, in terms of like if they were talking to each other over video?
That's the last set of slides that I've got.
Okay, so I'll wait.
And you tell me if we've reached a point where we've tried your audience's patience too much, or if you want to do the video.
Oh no, I definitely want to do that.
Okay.
But let me just, can you clarify though? Is now a good time? In other words, unless you already were planning and you've got something where you're going to bring this up, this issue of, wait a minute, if they're disagreeing on when things occur, like couldn't the guy who thinks it already happened tell the other person and give them that information? And so what does that mean?
The answer to that is that when we talk about the times that Bob attributes to events, that's not the time when he sees the event. It's the time when he thinks the event happened. Look, if you're looking at the sun and you see a sunspot develop, if you understand a little bit about how light works, you realize that that sunspot did not develop at the moment you saw it develop. You developed 8 minutes earlier because it takes light 8 minutes to get from the sun to you. So Bob says that sunspot formed 8 minutes ago. That doesn't mean he saw it 8 minutes ago. That means that after he sees it, he figures out that it happened 8 minutes ago. 8 minutes ago when it was happening, he didn't even know about it. Mm-hmm. And it's the same way here. Bob and Alice are going to disagree about simultaneity of events. Alice is going to say that car crash happened at 3 o'clock, and Bob says, no, it happened at 1 o'clock. And your question is, well, if Bob says it happened at 1, why doesn't he tell Alice about it at 2? And then she knows it happened before 3. Answer, he doesn't know about it yet at 2. When he finds out about it, he calculates that it must have happened at 1. But he does not know about it in time to actually be able to tell Alice about it. So we don't get a contradiction where she knows about something before she thinks it happened.
Yeah. So that was another thing that you stressed in the book that really made it click for me, like to understand how can they be disagreeing on the order of events, and that once like there's long, vast reaches of space and it takes a while for the light to travel. And so when you're getting information and then you're calculating and saying, well, based on where I think the thing is, it must have happened, that I think it makes more sense for people to realize how could it be that they can disagree on the chronology of events. And that's part of the explanation.
Okay, so this is at Bob's request. Bob wrote to me a few days ago and said he would like to see what happens if Alice and Bob, the same journey, see what happens if Alice and Bob are communicating by video through the entire thing. And I think it's going to be easier when I think about video. I don't want to think about a 20-year-long video. I'd rather think about a 20-second video. So I'm just going to change all these times to seconds, and I'm going to assume that Bob has traveled 6 light seconds as opposed to 6 light years. I'm just calling things seconds instead of years because it seems more natural to me to talk about a 20-second video than to talk about a 20-year video. So Bob's making a short trip out, and here's Bob. Alice is going to transmit video to him throughout his entire journey. And every 2 minutes on the video, okay, I called them minutes, apparently not seconds. So every 2 minutes on the video, she's going to wave. So here is Alice. At time 2, she waves. At time 4, she waves. She's also going to wave at time 6, 8, 10, 12, etc. These gold lines are the signal from the video traveling toward Bob. This is Bob on his outbound trip to the star. This is Alice every 2 minutes. Well, she's sending video continuously, but every 2 minutes on the video, there's a picture of her waving. And those signals from the video travel at the speed of light out and catch up with Bob as he travels toward the star. Now, the first thing to say is that Alice is waving, according to her, every 2 minutes. But according to Bob, she's going to be waving less often because he thinks her clocks run slow. In fact, he's going to say she waves every 2.5 minutes. Here is a grid line from Bob's frame. This is the line t prime equals 2.5. That happens to pass right through the point where Alice's first wave. So Alice says, I'm waving at time t equals 2. Bob says, no, you're waving at time 2.5. When Alice says time 4, Bob's got a grid line through there saying that that's time 5. These points on Alice's frame are labeled 2, 4, 6, 8. On Bob's frame, they're labeled 2.5, 5, 7.5, 10. I only drew one of Bob's grid lines, but if I had drawn more, they would have been 5, 7.5, 10. So Bob says that she's sending video at 80% speed. That doesn't mean he's seeing it at 80% speed, because as he travels outward, each signal takes longer to reach him. He keeps being farther away. He's farther away, and as he gets farther away, those signals have farther to travel. So that's also going to, in addition to the fact that her clocks are running slow, there's another reason he's going to see the video running slow, because each signal travels farther to get to him. And so her signals actually arrive every 4 seconds, and he's seeing the video at 50% speed. Here, for example, here's the first signal. It reaches Bob at this point here, and on Bob's grid, that's at time 4. She sent it at time 2, it arrived at time 4. Here's one she sends at time 4, it arrives at time 8. On Bob, which you can see on Bob's grid line there. I have interchanged seconds and minutes here. My apologies. Okay. Seconds and minutes mean the same thing.
Yeah.
She says, I'm sending these every 2 minutes. Bob says, no, you're sending them every 2.5 minutes, and I'm getting them every 4 minutes. And that continues up to this point where I turn around. Now, when I turn around, from now on, each
Can I stop you?
Yes.
Steve, I just want to make sure people are tracking this distinction there. Is this true? Because for one thing, am I right in saying the speed of sound, in air is constant?
No.
Okay.
No, not constant according to different observers. Different observers will. Speed of sound relative to the air. We can both agree on what it is relative to the air, but not relative to ourselves.
Right. So what I'm getting at is if I'm moving away from somebody at 3/5 the speed of sound and he's clapping every 2 minutes, would that affect how often I hear the?
Yes.
Like,
So,
that's what I'm trying to.
Allison's video looks slow for 2 reasons. One is that according to Bob, her clocks are running slow, and second, he's running away from her.
Right.
If it were sound, we would have the second effect, but not the first.
That's what I'm getting at. So
it would be slow, but not as slow.
Right. And so what I'm getting at is that effect is there. That if with a sound thing, someone's clapping, and then you're going at a significant fraction of the speed of sound, you wouldn't be hearing the claps as frequently. But you wouldn't therefore conclude, wow, I think the time is running slow for that guy. You would just say, no, he's clapping it the same amount. It's just I'm moving away from him, so it's taking a while for the sound. You're saying
exactly,
Bob, like he's taking into account that I'm moving away, or she's moving away from me rather, and so every wave takes longer for the light to reach me. But even after he accounts for that, he's saying, whoa, but she's late. She's waving.
He's saying there are two with the sound. There would be one thing going on, and so the sound would be slow, but it would not be this slow. This is more slow. One, the fact that Alice's clocks are running slow is slowing the video down to 80%, and then the the fact that he's moving away is slowing it down to 5/8 of that.
Okay.
So you're down to 50%. But now when he starts back, those video signals each one is going to start reaching him sooner than the last one because he's getting closer and closer to Earth. So now the picture, I'm going to not change this part, but I'm going to add the return journey. Here is Bob's return journey. Here are Alice's signals going out every 2 seconds, according to her. And the first two, it gets the interval between them reaching Bob is 4 seconds. The first one takes in between the first and the second, 4 seconds pass. On his way back, he still says Alice's clocks are running slow, which slows the video down. But he also says, I'm getting closer and closer to her, so each signal takes a shorter time to get to me, which speeds the video up. Which effect wins? It turns out that the second effect wins. He is now seeing the video at double speed. She's sending signals every 2 seconds according to her. They are arriving at times 9, 10, 11, 12, 13, every 1 second according to him. So we've got two effects. One thing is making the video seem slower. One is making it seem faster. The second effect wins, as it turns out. And he's now seeing, and again, how do I know the second effect wins? There's a lot of detail on that in the book, which I'm leaving out of the video. So here I'm just telling you the punchline rather than explaining the joke, but the book explains the joke. So this is the picture, and look what's going on here. She waves 10 times. Bob sees 10 waves. When Bob gets home again, his account took me 8 minutes to travel out, 8 minutes to travel back. During that time, she sent 10 waves. I saw them at time 4 and time 8. That was really spread out. And then I started my journey back, and they started coming really fast. 9, 10, 11, 12, 13, 14, 15, 16. There were 10 of them. We both agree there were 10 of them. She says they happened regularly, 2 times 2, 4, 6, 8, 10, 12. I say they happened at times 4, 8, 9, 10, 11, 12, 13, 14, 15, 16. But we both agree there were 10 waves. I saw the whole video. I saw part of it slowed down and part of it speeded up. And it turned out that that all canceled in such a way that I managed to exactly see the entire video over the course of my trip. Nothing was left out. The entire video played on my screen. I watched the whole thing. It was really, really dragged there at the beginning, but then I really had to pay a lot of attention to keep up over the second part of it. I get home once again, just as before. It's the same picture as before. He's aged 16 years. She's aged 20. They both agree that she sent this video. They both agree she waved 10 times during the video. They disagree about the times when Bob received those signals. They disagree about the times when Bob saw the waves on the videos. They disagree about the times when Alice made the waves. But they both agree that the waves took place. They both agree that Bob saw them. They both agree that Bob is home. And they both agree that Alice is 4 years older than Bob.
Great. And so...
And I'm pretty sure that this picture is not in the book, and it should have been. So I will apologize.
Yeah, I mean, this is great. I mean, it's saying intuitively, people are trying to figure out, like, this is called the twin paradox, folks, that, that they're identical twins. Then one guy goes out, comes back, and he's younger than his identical twin. So it kind of makes sense to tie to the earlier story that, yeah, if like every one of her birthday parties, she sent him a video, like, thinking of you, I just had my birthday, that it would make sense that, oh yeah, going out to the star, he's celebrating his own birthdays on the ship more frequently than he's getting it from her. And then when he turns around, since we know it's got to be when he steps off the ship, she's old and he's young, he must all of a sudden see a bunch of birthdays piling into his inbox. So like this pattern, you realize that something like that must be going on. But again, I don't know if this is unfair to spring on you, but in like a Galilean framework or a Newtonian framework, that effect would still be there, right? That as he's getting farther away, it would, but
Yes.
yet when he got off the ship, they would be the same age.
Yes, absolutely. In a Galilean framework, the video would run slow as he travels out, and it would run fast as he travels back, but not by these same amounts, because here we have
Right, okay.
overlaid on top of that the effect of his saying that our clocks.
Okay,
run
so
slow.
here, and this is the final thing, is so, before you had stressed how, like you say, well, how do you reconcile the fact that during both legs of the trip, she seems to be running slow from his point of view, but yet they both agree she aged more when he gets off the ship. And you're putting a lot of emphasis on, it's that one shot adjustment when he changes directions. So is there something that in the Galilean framework would not happen when he turns around, but it does happen in this framework?
When he turns around, his time grid lines don't change when he turns around.
Right.
You see it right here. This blue grid line, that's his time grid line just before he turns around. This green line, that's his time grid line just after he turns around. In a Galilean framework, they would both be horizontal. They would both coincide with the red line. And so there'd be no change there.
Would the video look the same, but just his calculations in terms of, wait,
The
how old
video-
is she really? Is that what's different between Galileo and Einstein when they're in the spaceship, or not?
So, yeah, the video looked the same.
I mean, intuitively, it's got to be like right when he's in outer Earth orbit. The video he's seeing, if it's Einstein looking at it, she has to be older.
He has to see the entire video over the course of the trip. Again, the calculation of exactly how much slower it runs is at the beginning, and how much faster it runs at the end is going to be different. But qualitatively, the fact that it runs slow at the beginning and fast at the end is still going to be the same.
Okay, let me. And I'm sorry, this is unfair, but is that difference the fact that we get, there could be lags or whatever, but kind of like if you have a slow internet connection, it's not that I actually think the guy on the other end, if he's talking like this, that he's having a stroke or something. So no, the Wi-Fi is screwy. But again, with the Einstein thing, it's like, no, when he gets back to Earth, she really is old compared to him. Is the constancy of the speed of light, is that intrinsically related to that? Like, is there some reason that how the video appears, and there must be a sense in which she does start aging faster?
The constancy of the speed of light, in order to get that constancy of the speed of light, I needed to draw the grid lines the way I drew them.
Mm-hmm.
The logic is there's only one way to draw the grid lines that will make the speed of light constant. The speed of light is constant. We know that experimentally. There's only one way to draw the grid lines that will make that be true.
Mm-hmm.
And then once you've drawn the grid lines, the picture tells you exactly what has to happen. If you had drawn different grid lines, the picture would have told you different things.
Okay. And I suppose just to stress, because I remember when I was young, Steve, and we got like the World Book Encyclopedia, and they had like the special science edition, and I was like in 7th grade learning this stuff. And I think I told my dad, and he didn't believe me. He was like, I'm sure he didn't doubt the, but he just felt like, no, a person wouldn't. But I mean, they've experimentally tested this, like with the decay of radioactive particles and stuff, right? Like, I mean, this is.
Oh yeah.
This isn't just some theory. Like
it's one of the most empirically verified theories in the history of the world. My parents were cheaper than yours, so we had the Book of Knowledge instead of the World Book. But and therefore, I was not as well educated as you at that age.
Okay, so this was great. Is there anything else you wanted to say or on this?
Just buy my book. Buy all my books. I just got word, actually a few minutes before we started taping this, that my Price Theory and Applications, which is now in its 10th edition, and I think by far its best edition, is suddenly on sale at Amazon for a fraction of its usual price for the remainder of the calendar year. This is the Kindle edition, normally about $100. It's $35 from now till December 31st. And so I hope people will look at that. I hope while they're at Amazon, they'll also look at the Relativity book. And there is one website where you can go to get links to all of my recent books. Maybe I can make another slide here and write the URL. Would that be
Sure
okay?
thing. Yeah, go ahead.
Let me see if I can figure out how to do it. New slide. Here we go. I hate this click to add title stuff that they automatically add, but www.landsburg.com/new books. And that will give you a link to the relativity book, a link to the price theory book, which is now, it doesn't say it on the page yet. I should put it on the page, but now on this incredible sale in the Kindle edition from now to the rest of the end of the year. And you'll also be able to read excerpts from both books at that site. And I think maybe read the prefaces and read some other excerpts. Yeah, and I hope people enjoyed this. I always, I know your audience normally comes here for economics, so I'm not sure this is what most of them were looking for, but I hope we gave them some fun.
Well, it is going to be, and I don't care what they want because this is what I wanted. But also, I will say on my YouTube channel, is it Grothendieck? How do you say that guy's name? Grothendieck. That off the top of my head, I forget, but that's one of my most popular videos. And not because the others have 8 views and that has 16. Like there's a deep fan base for that guy, I guess, and people searching for his name found that video and loved it. So
cool.
Well. So thanks, Steve. I guess the last question is, are you going to do one on general relativity?
I started writing a book on general relativity something like 30 years ago. The plan was 6 chapters. I have 3 written. I feel like I have...
are you writing a chapter every 2 minutes and then just... or not?
I suspect it's never going to get finished. But it's on my list of things that I would like to finish.
Okay, well, that would be great if you can find it in your stamina to bang that thing out. I'd love to see, because again, you really clarify. I've been reading a ton of stuff over the years on this, and this was great. Well, folks, my guest has been Steve Landsburg. His book is Understanding Time and Space. He's also got his excellent price theory book that he just told you about. So go check out his stuff. Thanks, Steve, for your time.
Thank you, Bob.
Thanks, everybody, for tuning in. We'll see you next time.
You've just experienced another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. For more information and to subscribe to this podcast, visit bobmurphyshow.com.